All right, here we go. Day 2, differential equations. We're going to talk about separation of variables. This is probably the easiest differential equation solutions you'll find. We'll find a general solution, which will have a plus c, and then a particular solution, which will have an initial condition given. Okay, so dy dx equals x cubed plus 3, okay, with an initial condition. Right there, it's your initial condition. We'll get to that in a moment. So if dy dx, we'll do some of our work down here. If dy dx equals x cubed plus 3, then dy equals x cubed plus 3 dx. So we integrate both sides. This is why these are the easy problems, right? We get y plus c equals x to the 4th over 4 plus 3x plus c. Alright, and for the purposes of this, all I'm going to do is I'm going to bring this, let's call it c1 and c2. I'm going to bring and subtract this one over, and what you'll see is that I just get some other arbitrary constant, so we're good. So now I take into consideration my initial condition 2, 1. So that means y equals 1 when x equals 2. And that's going to help me to find c. So it looks like 1 equals 16 over 4, which is 4 plus 6 plus c. Therefore, 1 equals 10 plus c, so c equals negative 9. So now I can write my particular solution for this. It's going to be this with negative 9 plugged in for c. So I'd have x to the 4th over 4 plus 3x minus 9. That would be our solution with that initial condition, whose derivative is dy dx. Alright, so I'm going to clear this out. I guess I can't. I would like you to try example 2, and I'll come back with the answer. Okay, so that one wasn't very fair, so I'm going to walk through this one with you. Okay, so notice that I don't have an x involved, so what I'm going to do is I'm going to divide both sides by y plus 3 and multiply both sides by dx, and then I'm going to integrate that with an initial condition of 4, negative 2. So what would I get here? I'd get the natural log of y plus 3 plus c, which I'm going to end up bringing over to the other side, equals x plus c. Okay, so did you follow it? I just integrated on both sides. That would be the natural log of y plus 3 plus some constant, and then the integral of 1 dx would just be x plus c. Alright, so now I insert my initial condition, which is 4, negative 2. So that means when x is 4, y is negative 2. Oh, that's nice. Why? Because that becomes natural log of 1, which means that 0 equals 4 plus c, which means that c equals negative 4. Therefore, I'm going to go back up to here. I'm going to put a negative 4 in for c. So the natural log of y plus 3 is equal to x minus 4. Now we got a little bit of work to do because we have to isolate y. So I'm going to take e, and I'm going to take e to the power of x minus 4. So y plus 3 equals e to the power of x minus 4. Okay, and then just subtract 3. So e to the x minus 4 minus 3. That's the solution, particular solution to the differential equation with the initial condition 4, negative 2. Alright, more separation of variables. Now we got both x and y involved. I'm just going to pick one of these. I'm going to go with what looks to be the uglier of the two, and I'll go with number 4. So if I separate these variables, I have to divide by y and multiply by dx. So I'll get 1 over y dy equals 1 over x dx. Okay, so that's why we want multiplication. We can't have addition or subtraction of two variables at all. Otherwise, we have to use a different method, which we'll get to later in the chapter. So if I integrate both of these with respect to their given variables, I get the natural log of y equals the natural log of x plus c. Alright, and at this point, there's not a whole lot of simplifying I can do. So what I'm going to do is when y equals e squared, x equals 6. So when y equals e squared, then x equals 6. Alright, so I have to figure out a way to isolate this. Ooh, this is handy. That's actually 2. The natural log of e squared is just 2. Natural log of 6 plus c. This is not nice. So I'm going to rewrite, I'm just going to write it over here. 2 minus the natural log of 6 equals c. I guess I could have squeezed this together if I wanted to. Remember, this was the natural log of e squared. And this I could make more compact and write as natural log of e squared over 6 equals c. I guess I could do that. Yeah, I guess I could do that. Okay, so I know c equals that. So I can plug that in directly right here. So the natural log of y equals the natural log of x plus the natural log of e squared. E squared over 6. Ooh, I could do a nice little squeeze this together. Hold on a second. Let me simplify this to the natural log of e squared x over 6. And to solve for y, I would just take e to the power of both sides. And, oh, convenient. E to the ln of any power. Right? E to the ln. As long as e, this base, and this base are the same. That's true. Boom, that's really cool. That was a nice one. All right, really cool. So that would be the function whose derivative would follow y over x. That's really cool, specifically at that point, at that initial condition. All right, let's try this one. We'll do one more, figure out where we're at. It's multiple choice, apparently. Why don't you try this one on your own? I'll do it on the side. Okay, so I have y dy equals x squared dx. So that's y squared over 2 equals x cubed over 3 plus c. This notation right here is a little bit funky, right? Y of 3 equals negative 2. That just means when x is 3, y is negative 2. That gives me an initial condition, or a constant of negative 7. So I get y squared over 2 equals x cubed over 3, okay, minus 7. So let's see if we can work that out a little bit here. I'm going to multiply both. I'm seeing something I like here. I don't see an e at all. That's out. That's out. I'm going to guess that this is out. And I'm going to work my way between these two, and they look very similar. One's positive, one's negative, so let's see what happens. So I multiply both sides by 2, and I get y squared equals, looks like 2x cubed over 3 minus 14. And then I take the square root. Now, when you take the square root, you're going to get two values, plus and minus, right? There's something sneaky going on in this problem, and the sneaky thing is that our y value in this case comes out to be negative, right? So that means our y values have to come out to be negative. So d is out, and therefore, since we have that negative y value, e is our answer. All right, we're going to do separation of variables with Euler's method tomorrow to estimate the value of some known function. So let's move on, maybe do a homework problem. How about, there's an Euler method. Given the initial condition this, find an approximate value using Euler. No. How about this? The tube of a cross-section shown has an inner radius of 3 and an outer radius of 6. Within the tube, water is maintained at a temperature of 100 degrees Celsius. Within the metal, the temperature falls off at a rate of that. So we've got a differential equation dt, which is temperature with respect to x, the distance from the center or central axis, is equal to negative 20. I'm going to rewrite this as x to the negative 0.63. Okay, so that would mean dt equals negative 20 x to the negative 0.63 dx. Now I can integrate. Okay, when I integrate, I get t equals negative 20 x to the positive 0.37 over 0.37. Don't forget plus c. Okay, so now is where my initial condition comes into play. At the very outer edge, it looks like, actually I'm sorry, at the inner edge, when the distance from the center is 3, so at a point like that, the temperature is 100 degrees Celsius. So we're going to plug and chug a little bit with that so we can find C. So if I were to plug those in, that would mean I'd have 100 is equal to negative 20 times 3 to the 0.37 over 0.37 plus C. We're going to utilize this to find C. I used my calculator and I found that C equaled 181.163. So then this function t equals negative 20 x to the 0.37 over 0.37 plus 181.163 is our particular solution. Now what we want is we want to know the temperature. We want to know the temperature when x equals 6. So we do a direct substitution. We want to know the temperature on the surface. And therefore, when we use our calculator, we see that the temperature, 6 centimeters, or whatever that measurement was, from the center of the whatever this piece of metal is, would be, I used my calculator, got this. Alright, you guys, differential equations and separation of variables have a lot of applications, so hopefully that was understandable. We can go over questions if you got them.